First of all, I would like to thank Dheeraj and the organizers for inviting me here. The goal of this talk is to describe our efforts in estimating primordial non-Gaussianity, imprints of primordial non-Gaussianity generated in loop quantum cosmology in the cosmic microwave background. This is a work which I did with my student Roshna. So loop quantum cosmology is an attempt to extend inflationary regime to the Planck era. So in this scenario, prior to inflation, there is a bounce. So the universe started in a contracting phase. There was a contracting phase before the bounce, and after the bounce, universe accelerates. So the background dynamics is governed by modified Friedmann equation. As you can see, the Friedmann equation has been modified with nonlinear terms in density, and there is a supremum density in the theory. If rho is equal to rho sub, a dot is 0, and if you compute a double dot at rho equal to rho sub, you will see that it is actually a minimum. And if you have a suitable potential, you can have bounce and then followed by inflation. So the background dynamics is illustrated here. So scale factor decreases to some value and then starts expanding again. At late times, you have an inflationary epoch. So there is a bounce followed by inflation. And energy density does not go to infinity as in GR. Energy density reaches a maximum value, which is rho sub. And this is the evolution of scalar field. So idea is to study evolution of perturbations in this background. So we will assume that perturbations are test fields living on this background. So we consider fluctuations to the scalar field, and we want to we treat them as quantum fields. So we expand we promote them to operators by expanding them using annihilation and creation operators in terms of the classical solutions. Phi k are the mode functions. So basically we are interested in quantifying this perturbation and to study what are the observables, to tie them to observables in the CMB. So we need to study correlation functions. So the correlation functions that we will study are 2-point functions, 3-point functions, and so on. So this is how you can define the correlation functions of, in this case, 2-point correlation functions of delta phi. And you can see that the 2-point correlation function, so basically this is how you define the power spectrum of 2-point correlation functions of scalar fluctuations in the scalar field. So it is often convenient to work with another variable known as curvature perturbations, which actually freeze once they exit the horizon. So it is convenient to work with them, and we will express this power spectrum of scalar fluctuations as in terms of the curvature fluctuation in this manner. So similarly, you can compute 3-point correlation. Okay, 3-point correlations. If you have an interaction Hamiltonian at third order, you can compute the 3-point, at least the tree level 3-point correlation using this formula. So basically, you have to evolve the mode functions throughout the throughout the history, that is across the bounds and through the inflation, and you do this integral and you can compute the 3-point correlation. Again, this is the 3-point correlation of scalar fluctuations. What we actually want is to compute the 3-point functions of curvature perturbation, and you can relate the 3-point correlations in delta phi, which is the fluctuations in the scalar field, to the curvature perturbation to 3-point function in curvature perturbation. So we will talk about two quantities often interchangingly. So one is bispectrum. Bispectrum is basically the 3-point correlation of curvature perturbation sans the delta function, Dirac delta function. So this is a function of three wave numbers with one constraint, so 2 wave numbers. And we will also talk about the often the 3-point correlation of curvature perturbation is quantified by FNL, which is a dimensional quantity, which is basically the ratio of 3-point correlation to square of power spectrum. So as I said, we want to study this 3-point correlation as well as 2-point correlation in LQC. So the evolution, it depends on, basically we want to understand what is the evolution of perturbations throughout this background where you have a bounce followed by inflation. Okay, so so we can write the evolution of perturbations. This is the Mukhanov-Sasaki variable, which is related to the fluctuation in the scalar field using this formula, and it obeys a time-dependent harmonic oscillator. And so to understand the dynamics, it is convenient. It is illustrative to compare k with behavior of root of absolute value of omega k. And so this is what is plotted here: root of omega on y-axis, and this is the dark black solid line, and this is time. T equal to 0 is the bounce, and all these dashed horizontal lines are different scales, different wave numbers. So you can see that there are two scales that are characteristic in the problem. One is the scale called as KLQC. KLQC is actually related to the maximum value of energy density at the bounce, and Ki is the inflation, is the mode set during inflation. Modes smaller than Ki are never excited, so they are always super Hubble in the inflationary language. And K star is the pivot scale, and here we will take K star to be 0.002 MPC inverse. So as you can see from this figure, if you have a mode which is lying here, that mode is that particular mode will always be much greater than root of omega until it crosses the horizon during inflation, or crosses this potential during inflation. So what happens is that for those modes, they are not sensitive to the what happens at the bounce. So those modes, those large wave numbers or small length scales don't feel the effect of the bounce, and they just are amplified during inflation. So those modes are expected to be scale invariant as you find in slow roll inflation. Now modes which are sensitive to this peak this potential or this root of omega during the bounce, they are comparable to they are modes that are comparable to KLQC or smaller than them. They will be excited during this bounce. So what will happen is that they will be excited. So by the time they reach somewhere here, which is before around the onset of inflation, they will already be in excited state. And not only that, if you look at correlations, they will also be non-Gaussian by the time they reach before they reach the onset of inflation. So what happens is that the job that inflation does is they amplify whatever has been set during the bounce. So modes which are sensitive to K, which are comparable to KLQC, will be excited. They will not be they are not expected to be scale invariant. Okay, and there are these modes which are K much less than Ki, they are never excited, so they remain in the Minkowski state because K is much smaller than this. So B is proportional to the potential. Okay, so as in terms of curvature perturbation, they are not amplified. So this is the qualitative picture that you can understand from this analyzing this equation, and that is what we numerically find also. So what we do is we impose initial conditions somewhere here, where most of the observable modes are adiabatic, or K square is much greater than omega, and we evolve the perturbations through bounds across the inflation and compute correlations. I mean, sometime later during inflation. Okay, so this is what we do. And these are the numerical results. So as I mentioned, so this green dashed line is the slow roll result. So modes K, which is much greater than KLQC. KLQC is denoted by this vertical dashed line. They are scale invariant because they don't feel the effect of bounce at any time during their evolution. Modes which are comparable to KLQC or smaller get amplified, and the modes which are smaller has this modes which are much smaller than Ki or comparable are not amplified. So this is the so these are the observable scales. So most of the work in which analyzes the power spectrum of LQC are done with the hope that perhaps we can this portion of the spectrum will leave some imprints in the observable universe like CMB. Now, so let's look at primordial non-Gaussianity. Primordial non-Gaussianity, as I mentioned again, mentioned earlier, the large scale modes are are scale invariant. Large k are scale invariant, so they have slow roll like spectrum. Modes which are sensitive or which are comparable to KLQC or smaller are not scale independent, scale independent. So they are actually oscillatory, and as you can see from the amplitudes, they are highly non-Gaussian. And you can. There is one more thing that you can see from here. This is that this departure from scale invariance starts at this around this wave number, whereas power spectrum for power spectrum the departures from scale invariance arises here. So you can see that FNL is actually more sensitive to, or 3-point functions are more sensitive to the bounds than the power spectrum. This is expected because they you are actually integrating through the bounds in computing the 3-point function. Okay, so now our goal is to compute, take this bispectrum and compute the reduced bispectrum, which is observed in CMB. So the idea is that you have to so in order to compute reduced bispectrum, where this x, y, z are either temperature or electric polarizations, you have to do this 4-dimensional integral, one integral over k1, k2, k, I mean 3 integrals over wave numbers and one integral over x. So you have to do this 4-dimensional integral. So if I take the numerical result, numerical calculation, such a bispectrum, and try to plug it in here, and then do the calculation, then what my problem is that for each k I have to do the numerical simulation, and there are, so and even if it's a very flat constant FNL, for each k if I have to do the not constant, very simplistic FNL, and if I have to do it for each k, it is time consuming, and in this case it's oscillatory, so if I have to resolve the numerical bispectrum, it's going to be tedious. So what we did is we try to estimate come up with an amplitude, come up with an analytical template to explain the bispectrum. So this is the bispectrum, right? So primordial bispectrum, this is what we have. So you can split it into 2 parts. One is you have a near scale invariant part, which is the slow roll part, or we will call it the local part, and then oscillations with some shape on top of it. So we will split into 2 parts. So the local part is easy to simulate, I mean to model. So we just take the local template. So with a constant value of FNL, FNL set to 10 raised to minus 2. Okay, and then you have this local template. So that explains the local part. Now how do you estimate the this behavior? So what we did is, okay, so bispectrum has basically an integral. Okay, so you can roughly write it as Vk by Z. There are 3 modes which are you are computing the bispectrum at the end of inflation or later towards later part of inflation. So you have an integral from eta I to eta f, and inside the integral you have a term which is time dependent, and then you have a function of mode function, maybe it's derivative or mode functions. So what we did is so simplify the whole thing. So you keep the time dependence term as such, but you say that maybe this function all I need to care is just simplify this by product of the mode function. Of course, there will be some functions of factors of k square and all. For now, we are just ignoring it, and we will see what we get. And then we also assume that Vk is basically given by e raised to minus ik eta. Okay, so this is true when k is much larger than KLQC, but not true in general. But we are going to simplify this by e raised to minus ik eta. So if I do this, plug all these assumptions in, my integral that I have in the bispectrum expression can be written in this manner. And I am also only interested in the portion around the bounds, because I am interested in finding the contribution from the bounds. So I have an integral from minus eta naught, which is some time before the bounds till some time after. And of course, I extend that integral to minus infinity to infinity by introducing a window function, which only selects that time regime around the bounds. Now, the good thing about writing this integral in this form is that I can actually use Cauchy residue theorem to evaluate it. Now, then basically Cauchy residue theorem tells you that you just have to look at the poles of this G, and whatever the poles are, you compute the residue from that. So G can have either a real pole or an imaginary pole. If you have a real pole, then this is just oscillatory. But if you have an imaginary pole, you will get the some shape. Okay, so you look at, so the motivation is what is the imaginary pole. So if you get the imaginary pole out of it, then it will, so remember this is all done with an eye on the numerical result. So you know that it has some behavior which is decaying and then the oscillatory part also. So that pole, if the real pole will account for the oscillatory part and the imaginary pole will account for the decaying behavior. That is expectation, or that is so what we can see is if G has a scale factor at the denominator, and then because A is a minimum, you can see that there is definitely a pole which is actually imaginary, because if you Taylor expand the scale factor, you can see that eta is equal to root of minus A by A double prime evaluated with bonds. Because it's a minimum, A double prime is positive, A is always positive, so that is an imaginary pole. And there is some analytical expression that you can compute for the scale factor around the bounds and use that to extract the pole. And you get that the pole is located at this value. And we say that the scale dependence, okay, so now if you compute the residue, you plug it in the pole in this eta, and then you can say that the scale dependence of the imaginary, so if scale dependence of the bispectrum is basically this, okay, at least the decaying part from the imaginary pole is this, okay. This is a overly simplified way of looking at it, but we'll see. So then there are other things. We don't actually play with the oscillatory part, but we just include an oscillatory feature by saying that the oscillations are modeled by sine of k1 plus k2 plus k3 divided by, and the scale of oscillations is ki, which is the lowest value of ki that is excited during the bounds as well as inflation. And there are these modes which are evaluated at the end of inflation, and we just replace them by the power spectrum. And then if you put all of them together, you can compute, you can express the bispectrum in this form, okay. And here there are power spectra, so because power spectrum are also numerical results, so we want to substitute by analytical result, so we give this power law, pieces of power law, broken power law kind of thing. So putting everything together, we have this bispectrum. Of course, computing the FNL, and of course, how good is the analytical? Because we have used a simplified argument to compute the bispectrum, but what we find is that the analytical template actually explains the primordial bispectrum quite well. So now the challenge is to compute reduced bispectrum. And what we, so the good thing about this template is that it has, if I have an integral over k1, k2, k3, none of them speak to each other. So I can separate them out. I can do the k1 integral separately, k2 integral separately, k3 integral separately. So I can do that, and I can express, so 4-dimensional integral actually splits into one integral over x, and then another integral over k. So I just have to do the k integral once, and then I have this. So this template also has a separable property, and we compute the reduced bispectrum. And what we find is that this is the contribution from the local template, and this is the contribution from the highly oscillatory part. So it turns out that because of the high frequency oscillations in the spectrum, the k integral over k will actually wash them out. And so we see that even though primordial bispectrum is non-Gaussian, the observed reduced bispectrum will be consistent with whatever we have observed today. We have repeated this for TTE and EEE correlation, and we get similar results. So I'll leave you with the summary. So in LQC, the primordial perturbations are non-Gaussian, yet at the level of reduced bispectrum, it is Gaussian. Thank you.
Thank you. So maybe one quick question.
Okay, I'll just repeat what we
yes.
discussed a couple of weeks back when you came. So the signal you have is fairly large. It's just that there's a sine problem, sinusoidal oscillation, right? So there's nothing that compels you to measure only bispectrum as defined by the general community. You can always define a quantity where this signal is actually added up. And the challenge would be to now look for that in the data. I mean, to me, it's a eminently doable, thing, and it's a huge signal. So I think I strongly feel that you should look into it. I mean, it's just to me it's very doable.
Yes.
Basic general question.
Uh-huh.
NQC models, what of inflation? What do you get for R?
What that depends on the tensor. I mean potential.
So,
that you have.
so this model doesn't make any ab initio prediction for R.
It depends on, because there is a inflation. Inflation follows after the bounds. No, so the tensor to scalar ratio at whatever scales we are measuring will depend on the model, underlying model.
Okay, so it depends on the inflationary model.
Inflationary model.
It doesn't depend on the
doesn't-
LQC details. Okay.
Okay, let's continue the discussion to the tea times. Let's thank the speaker again.